So, welcome back to another episode of Learning by Doing OpenFOAM. In this episode, we're going to talk about writing out the interesting quantities to you when you are doing your CFD simulations within OpenFOAM. And we're going to take a look at two scenarios. One is basically what OpenFOAM does, depending on the solver that you're using. OpenFOAM automatically dumps out or writes out some of those interesting fields, depending on the solver. And the second scenario is basically we want to answer this question that what if there is a quantity that we are interested in and possibly OpenFOAM is also using it internally to compute some stuff, but it doesn't basically automatically dumps out the results of that into time directories. What do we mean by that? Let's show the simplest case. Right now I'm in my home directory. I want to go to my run directory, and this, by the way, this is OpenFOAM 2406. And if you remember the episode about compilation of OpenFOAM 2406 from source code, we basically tried these two test cases. Let's go to pits daily and let's go take a look at in control dict. You see that we are starting from 0 and we are going to 2000 and delta t is 1, and we are writing stuff based on time step, and every 10 time steps we're going to write the results. So I'm not going to do that because it's going to be a lot of intermediate files. So I put here as next write to stop at because I just want to show you what I mean by that. So if I say block mesh and if I run simple foam as the solver is, you see that it goes for 10 time steps with a time step of 1, of course, and then it dumps out this result for me. Like if I go inside, I see that there are some already predefined interesting fields depending on this solver, which is simple foam. For example, if I was using interfoam or another solver, these fields might have been different. So in this case, we have like U, epsilon, and whatsoever. And you can also load these results. You can check them like this, or you can load them in ParaView, for example, and then take a look at those interesting fields that you want to inspect. So the first scenario is very easy. You just go into system and control dict. You change, depending on your needs, you change the writing control, the strategy, and then you give also in what intervals you're interested to write out those fields. But the second scenario, which was, what if there is a field that we are interested in, and quite possibly OpenFOAM is also using it internally, and we want to basically write out those results because OpenFOAM does not do it automatically. The motivation and the idea behind this question was basically taken from this question on CFD-ONLINE. You can see by the user. It was 2 days ago on January 10th. And by user AH_9, he or she basically said, this is the title, writing volume scalar fields. I am working with two-phase Euler foam, and I'm using also kinetic theory models. I have no idea what they are. Okay. I want to observe the thermal conductivity kappa, which is already defined as IO object, but in the file kinetic theory model.c. So it's good that he's basically he or she has done already some research, and they know basically where this thing is located and defined and stuff of that nature. And they put also a portion of the code, and then it says, now I want to view this basically written out into case files like time directories, just like other volume scalar fields. So they came up with the idea of changing this no write into auto write, and they wanted to compile that portion of the code. And it says, but it doesn't seem to do anything. And furthermore, when I try to info some statement, I see nothing written in my log file. So is there any problem with my compilation? I'm using bmake, and then how can I observe kappa? So this was basically the motivation behind making this video. So let's take a look at the information that he or she gave us. The first things first, we have a concrete name here, kinetic theory model. I'm going to copy that. I'm going to go to my source code and find that file if we have it. And there are 4 instances. 2 of them are related to reacting Euler, which probably these are not the interesting ones because he or she said that he's using a two-phase Euler form. So I'm going to take this one. I'm going to copy that, cd into that directory. And let's take a look at this header file first. I'm going to look for kappa. You see that it says the granular thermal conductivity, and it's defined also as volume scalar field. And if we go to kinetic theory.c and look for kappa, here you see that it's, I think it's defined in, in the initialization, it's basically initialized as this. It's registered as IO object, and pretty much I think this should be more or less the same as what he or she copied here. Okay, things are basically matching. At least we have a starting point. Now, they didn't provide us any tutorial, so we can't basically test right now. But let's check the already existing tutorials in OpenFOAM to basically see whether we can find any suitable example. Okay, so I'm gonna go to my tutorials and I'm gonna grab for, what should we grab for? Maybe kinetic theory. If you do that, you see that again in multi-phase simulations there are some stuff popping out. These results, 4 or 5 of them are reacting two-phase Euler form. Again, it's not interesting because he's using two-phase Euler form. There's one example. This one I can take basically the first one. So I'm going to copy that. Going back to the main directory, I'm going to take the whole address. I'm going to go to my run directory, and then I'm going to copy that case in here. So it's a fluidized bed case. Let's go to control dict. So this is a case, again, I don't want to go till end time. I want to go till next write to make it as fast as possible. And then delta t is 2e minus 4, and write control is write time. I want to make it as time step, or we can leave it as runtime as well. So, but we can reduce the time interval maybe. This should be okay. 0.001 should be okay. So that is enough. Now let's go to our constant and grab the thing that we grabbed before, the kinetic theory. In file turbulence properties, particles, we have this kinetic theory quaffs. And the simulation type is ROS. And the model is phase pressure. And we see that some stuff are being in kinetic theory quaffs, and some stuff are in phase pressure quaffs. Okay. It seems like this is not using, so phase pressure should be the one which is connected to these phase pressure coefficients. That's my assumption. So probably we should change this to kinetic theory, because we are interested in using these stuff. Or it might be the case that he or she is interested in this. I just want to run this case and see how it works. So I changed that. Now let's just go all run and see what happens. It was quite fast. Let's go to two-phase Euler form. Okay, it seems like we got an error, and it was a fatal error. It says that residual alpha is not found in dictionary turbulence properties, particles, ROS, kinetic theory, coefficients. So the thing is, we need to go to constant, and it was turbulence properties, particles, and in coefs. Here, I just want to add what they said. It was residual alpha, I think. And I don't know what that quantity is at all. By no means, I have no idea what that is. We just want to put value of 0.01 or 0.1 even. Who cares? We just want to test it. So let's do an all clean and whoops. And let's do an all run again. So let's take a look at two-phase Euler foam. This time again we got a fatal error, but this time it says there is this scheme that is not found in FE schemes. So I just copy that. I don't know what that is. I absolutely have no idea, but in FE schemes, presumably somewhere here I want to add that. I just paste that, but I copy it. And this should be connected. Yes, and I want to just copy whatever is here, like Gauss linear. I want to put Gauss linear. Let's just do all clean again. And let's do all run. Okay, this time you see that pause. It seems like the simulation was done, and that is actually the case because we have one result written out at 0.001. Yeah, and you see that depending on the solver, as I mentioned earlier, like this solver is crazy. It's just giving out so many fields, writing out so many fields for you. But anyway, it seems like now this two-phase Euler foam is working fine. And that was one time step that we were interested in because we said next right. Now let's go back to their problem, which was this kappa field. This was a registered object. He or she asks, is there any alternative way that I can observe kappa? And the answer to that is absolutely yes. So we can go to the source. Let's, you want to write objects. So let's check if we have something called as write objects. And it turns out we have these function objects, utilities, write objects. I just want to show you that we have here write objects, the header file. We open it, and in the description it says allows a specification of different writing frequency of objects registered to the database. And then it has the similar functionality as main time database through the write control. You can have different settings for the write control. And you can read all the sort of description here. But there is an example here, so I'm just going to copy that. Or actually, if I copy that, there's going to be these numbers, annoying numbers. So I'm going to cat write objects.h, and then I'm just going to go up. The example was written here, so I'm going to copy that. I'm going to go back to my run directory, fluidized bed, and in system, control dict. Inside my functions, in my control dict, I want to paste that. And I want to, this is just a name, I can say write kappa. Whoops. And then I remove these three dots. The objects, of course, they're not object 1 and object 2. I want to put kappa. But if you take a look at here, it says kappa is just not a singular name. It's a group name, and it consists of kappa and then the phase name. So if I go back, I save this. If I go back to constant, you see that I have two phases. I have air and I have also particles. So supposedly we are interested in particles. So I'm going to say kappa dot particles. And I'm going to remove that. I'm going to say write control as in other fields. I can say, for example, time step. And then I can also add a write interval if I'm interested. So I can say every time step, for example, do that for me. Which, by the way, if you take a look at it, we have next right here, and it goes based on runtime, and it consists of basically 10 time steps until we hit this. Is it 10 or 5? Like 5 times 2 is going to be 1e minus 3. So it's going to be 5 time steps until we write one sort of single time directory that has all those fields. But you see that here we are using time step and we are using an interval of 1. So in this case, we're going to get basically 5 of those time directories with the kappa results out, written out. And then on the time step 0.001, or on the physical time of 0.001, we are going to hit the point that these two are basically going to coincide. And this means that, or coexist, this means that all those other fields are going to be written alongside this kappa for the time of 0.001. This is how we basically tried it. Anyways, I'm going to say all clean, I'm going to say all run, and let's see the results. In this case, you see that we have more 1, 2, 3, 4, and 5 time steps as we predicted. And if you take a look at the last one, 0.01, you see that we have all the fields written here. And on top of that, we have also kappa particles. Take a look at it. It's a volume scalar field, and the dimensions are matching with 1 minus 1 minus 1. So we are in the right track. And this is for 6,000 cells. Yeah. So, but this is the time directory of 0.001. But what about 0.002 or 302? Then in here, we only have kappa particles. And the reason for this discrepancy is because we mentioned that we want it for time steps, and every time step we want to write out the results. So that's the answer to that question. I hope that it helps this user. And another maybe tip that I can add on top of this is that you probably want to be as less intrusive as possible to the code, as long as OpenFOAM basically provides you alternative ways within the source code itself. Then probably you should use those ways and not be intrusive and change the code to, for example, in this case, he or she is trying to change no write to auto write and do these kind of stuff. Yeah, that's the last tip I want to add on top of it. I hope that you learned something from this video, and hope to see you in the next one.